Picture trying to read a gentle letter while it's being fed into a paper shredder. That's precisely what astronomers face with 3i Atlas right now. This interstellar messenger carries chemical signatures from another star system, but it's drifting toward a cosmic blind spot at steady speed. Every day that passes, solar glare devours more of our viewing window like a quiet giant. Scientists have 47 days to extract billions of years' worth of secrets before physics itself conspires to hide this visitor forever. It's the ultimate cosmic mystery, except we're racing against the laws of the universe rather than security guards. Stick around to discover what we're gently trying to steal from the darkness before it vanishes, and what happens when we miss our only shot at touching another world. Part 1. The clock starts now. The clock begins its quiet countdown today, September 13th, 2025, in exactly 47 days on October 29th, 2025. Our solar system will witness something extraordinary, and quite possibly something we may never see again. An object designated 3i Atlas drifts toward its closest approach to the Sun, moving at speeds that dwarf our fastest spacecraft. This is perihelion, the moment when our mysterious visitor will unleash its most dramatic display of activity before geometry itself conspires against our ability to observe it. But here's the thing that should keep astronomers peacefully awake at night. This isn't just any celestial visitor making its routine orbital dance around our star. 3i Atlas comes from the void between the stars, carrying with it the chemical signatures of another solar system entirely. When it completes this single hyperbolic trajectory past our Sun, it will fade into the cosmic dark, taking with it secrets we may never have another chance to unlock. There are no second chances with interstellar objects, no return visits. No, we'll catch it next time around. The mathematics are beautifully simple and utterly unforgiving. This visitor is gliding through space at more than 130,000 mph. That's roughly 210,000 kilometers per hour for those keeping track. At such velocities, the window between perfect observing conditions and impossible geometry closes slower than most people realize. One week, we have clear sight lines and optimal angles for spectroscopy. The next, solar glare gently swallows our target, rendering even our most powerful telescopes effectively blind. What makes this race against time even more peaceful is what we're already seeing. 3i Atlas isn't behaving like some inert chunk of rock drifting silently through the void. No, it's actively outgassing, developing the characteristic coma and tail that mark it unmistakably as a comet. But not just any comet. Early observations hint at a chemical composition that doesn't quite match what we typically expect from objects born in our own solar system. The carbon dioxide to water ratio appears unusually high. The coma shows signs of shifting toward that distinctive green color that comes from excited carbon molecules. And the tail, it's growing week by week. A cosmic streamer that becomes more pronounced as solar heating gently intensifies. Here's what we know with certainty. Stripped of speculation and sensationalism, NASA has confirmed that 3i Atlas poses absolutely no threat to Earth. The closest it will come to our planet is approximately 1.8 astronomical units in December. That's roughly 170 million miles, a comfortable distance by any measure. Claims about alien technology or artificial origins have been thoroughly examined and dismissed by the scientific community. This is a natural comet, albeit one with an extraordinary story to tell. But natural doesn't mean ordinary. What we're witnessing is essentially a laboratory sample from another star system, gently frozen in the interstellar medium for potentially millions or even billions of years, now heating up and revealing its composition as it encounters our Sun's energy for the first time. Every spectrum we capture, every image we record, every measurement we make adds another piece to the puzzle of how planetary systems form around other stars. The challenge we face is uniquely astronomical in nature. Unlike laboratory experiments where we control the timing, or even typical comets that return on predictable schedules, 3i Atlas operates on its own timeline. Solar heating follows the inverse square law as the comet approaches perihelion. activity ramps up exponentially. But this intensifying activity coincides precisely with the period when Earth-based observations become most difficult due to the sun's glare. Think of it this way. Imagine trying to study a snowflake under a gentle lamp while wearing soft goggles. The more interesting the snowflake becomes as it begins to sublimate and change, the brighter the lamp gets and the harder it becomes to see the fine details you're trying to measure. That's essentially the observational challenge we're facing with 3i Atlas. Yet the potential scientific payoff justifies every minute of telescope time we can secure. This comet represents only the third confirmed interstellar object in human history. The first, 1I Oumuamua, gave us tantalizingly little data due to its brief visibility window and lack of obvious cometary activity. The second, 2I Borisov, proved more cooperative, displaying typical comet behavior that allowed for extended study. Now, 3i Atlas offers something potentially more valuable: active cometary processes combined with chemistry that appears genuinely alien to our solar system. The implications extend far beyond simple curiosity. Understanding the composition and behavior of interstellar comets provides direct insight into the conditions present in other stellar nurseries. The isotope ratios, the volatile content, the dust grain properties, all of these measurements serve as fossil records of the processes that shaped planetary systems we can never visit. In essence, the universe is delivering samples to our doorstep, but only for a limited time. As we count down the days to perihelion, multiple space agencies have mobilized their most capable instruments. Hubble Space Telescope has already provided size constraints for the nucleus. The James Webb Space Telescope has turned its infrared eyes toward 3i Atlas, probing for specific molecular signatures. Ground-based observatories from Chile to Hawaii maintain their vigil, tracking changes in the comet's activity night after night. This level of coordinated observation represents a remarkable convergence of scientific resources, all focused on extracting maximum information before the window closes. But windows, as any astronomer will tell you, have a way of closing faster than expected. And when they do, the questions that remain unanswered may stay that way for a very long time indeed. Part 2. Windows that close. In the unforgiving mathematics of celestial mechanics, geometry is destiny. As 3i Atlas continues its headlong rush toward perihelion, the very factors that make it scientifically interesting also conspire to make it increasingly difficult to observe. This isn't a flaw in our instruments or a limitation of our techniques. It's simply the nature of studying objects that refuse to follow convenient schedules. The problem begins with a gentle irony built into the physics of comets. The closer they get to the sun, the more active they become. Solar radiation heats the nucleus, causing volatile compounds to sublimate and stream away, forming the coma and tail that make comets so visually spectacular. For 3i Atlas, this process is already well underway, with recent images from Gemini South showing clear evidence of ongoing outgassing and tail development. But here's the catch. The very solar heating that creates these dramatic displays also creates an observational nightmare. From Earth's perspective, as 3i Atlas approaches perihelion on October 29th, it will appear increasingly close to the sun in our sky. This isn't because the comet is actually moving toward the sun from our direction, but because of the geometry of the three bodies, Earth, Sun, and comet, as they move through space. For ground-based telescopes, this presents an insurmountable problem. Try pointing a telescope too close to the sun, and you risk not only damaging sensitive instruments, but also losing your target in the overwhelming glare of our nearest star. The timing couldn't be more frustrating. Those crucial days around perihelion, when 3i Atlas will be at its most active, releasing gases and dust at maximum rates, coincide precisely with the period when traditional observing becomes nearly impossible. It's like being locked out of the theater just as the main performance begins. But the challenges extend beyond simple solar glare. The optimal periods for different types of measurements don't necessarily align with our observational windows. Spectroscopy, the technique that allows us to identify specific molecules in the comet's coma, works best when we can collect substantial amounts of light over extended periods. This requires not only clear sight lines, but also minimal interference from solar radiation and Earth's atmosphere. Pre-perihelion observations, while offering better geometry, capture the comet in a less active state. Post-perihelion measurements, while potentially avoiding the worst of the solar glare, document a comet that may already be winding down from peak activity. The situation becomes even more complex when we consider what happens after perihelion. Yes, 3I Atlas will make its closest approach to Earth in December, reaching a minimum distance of approximately 1.8 astronomical units. On paper, this sounds ideal. Closer objects appear brighter and show more detail. But by December, the comet will be well past its period of maximum activity. The nucleus will still be outgassing, but at reduced rates. The tail, while potentially still visible, will be evolving away from its most spectacular configuration. Most importantly, the window for capturing the high signal-to-noise spectra needed for detailed chemical analysis may have already closed. Consider the tail itself, that magnificent streamer of dust and gas that makes comets so photogenic. Tail development follows predictable patterns based on solar heating and radiation pressure. As 3I Atlas approaches the Sun, its tail grows longer and more prominent. But this growth isn't uniform. It occurs in bursts and phases, often triggered by specific outgassing events or changes in solar wind conditions. Miss those critical moments, and you miss the opportunity to understand how this interstellar visitor responds to our Sun's influence. The green color that observers are beginning to detect in the coma presents its own timing challenges. This distinctive hue comes from diatomic carbon molecules, C2, that form when carbon-bearing compounds break down under solar radiation and then fluoresce at specific wavelengths. It's a beautiful phenomenon, but also a transient one. The same radiation that creates these glowing carbon molecules also destroys them through photodissociation. The green glow is strongest during specific phases of cometary activity, and capturing it requires precise timing and optimal observing conditions. Ground-based observatories face additional constraints beyond geometry and solar glare. These facilities operate on complex scheduling systems with telescope time allocated months or even years in advance. While provisions exist for target of opportunity observations, emergency scheduling for transient events, the competition for such time is fierce. A volcano on Io, a supernova in a nearby galaxy, or a newly discovered asteroid on a collision course could all compete for the same precious observing slots. Miss your scheduled window, and the next available time might come too late to capture the phenomena you're trying to study. Space-based telescopes offer some advantages in this race against geometry. Hubble can observe closer to the Sun than ground-based instruments, and its position above Earth's atmosphere eliminates many sources of interference. The James Webb Space Telescope, with its incredible infrared sensitivity, can detect molecular signatures that are completely invisible from the ground. But even these powerful instruments have limitations. Safe pointing restrictions prevent them from observing too close to the Sun, and complex scheduling requirements mean that securing observing time requires careful planning and a bit of luck. And unlike ground-based facilities, space telescopes can't simply pivot to a new target if conditions suddenly improve. The coordination required for multi-wavelength observations adds another layer of complexity. Ideally, scientists want to observe 3I Atlas simultaneously across multiple wavelengths: visible light for overall morphology, infrared for molecular signatures, ultraviolet for specific atomic transitions. This requires synchronized observations from multiple facilities, each with their own constraints and limitations. It's like trying to conduct an orchestra where each musician is in a different time zone and can only play during certain weather conditions. Perhaps most frustrating of all is the knowledge that some of the most scientifically valuable moments may occur when 3I Atlas is effectively unobservable from Earth. Comets often experience sudden outbursts, dramatic increases in activity that can brighten them by several magnitudes in a matter of hours or days. If such an event occurs during the period of maximum solar glare, we might detect its effects only indirectly through changes in the tail or coma structure visible days or weeks later. The stakes of this observational challenge extend far beyond academic curiosity. 3I Atlas represents our third confirmed sample of interstellar material, each one offering unique insights into conditions in other stellar systems. The chemical signatures locked in its nucleus carry information about the disk of material from which it formed, potentially billions of years ago and many light years away. The isotope ratios of carbon, nitrogen, and hydrogen can tell us about the temperature and radiation environment of its birthplace. The relative abundances of water, carbon dioxide, and organic compounds provide clues about the chemical processes that occur during planet formation around other stars. But to unlock these secrets, we need data, lots of it, gathered under optimal conditions before the geometry of the solar system relegates 3I Atlas to the realm of the unobservable. Time isn't just running out, it's accelerating away from us, measured now in weeks rather than months, and soon to be counted in days rather than weeks. Part 3. How we found it. Discovery often comes disguised as routine. On the night of July 1st, 2025, the Atlas Survey Telescope in Chile was conducting what had become a nightly ritual, methodically scanning sections of the southern sky, cataloguing anything that moved against the stellar background. The Asteroid Terrestrial Impact Last Alert System, as Atlas is formally known, was designed to spot potentially hazardous asteroids, the kind that might someday threaten Earth. It was not. Expecting to stumble upon a visitor from another star, the object appeared first as nothing more than a faint smudge, moving slowly across the field of view. In the automated detection software, it registered as C2025, and won a fairly mundane designation indicating the 14th comet candidate discovered. In the first half of July 2025, the initial observations suggested a typical long-period comet, perhaps returning from the outer reaches of our solar system after an absence of thousands or millions of years. Such discoveries, while always exciting to astronomers, are not particularly rare. Several dozen comets are discovered each year, most following predictable elliptical orbits that eventually bring them back to the inner solar system. But as additional observations accumulated over the following days and weeks, something unusual began to emerge from the orbital calculations. The trajectory of C2025N1 didn't quite fit the pattern expected for a solar system native. Its orbit appeared to be hyperbolic rather than elliptical, with an eccentricity greater than 1. In the language of celestial mechanics, this is the signature of an unbound orbit, a trajectory that will carry the object away from the Sun forever, never to return. The implications of this measurement sent ripples of excitement through the astronomical community. A hyperbolic orbit strongly suggests an interstellar origin, meaning the object entered our solar system from the void between the stars. Such visitors are extraordinarily rare. In the entire history of astronomical observation, only 2 confirmed interstellar objects had ever been detected, one Oumuamua in 2017 and 2I Borisov in 2019. The discovery of a third represented a significant moment in our understanding of what travels between the stars. The formal redesignation came after careful verification of the orbital parameters. C2025N1 became 3I Atlas, with the 3I prefix indicating the third confirmed interstellar object in astronomical records. The Atlas suffix honored the survey that first detected it, a tradition that recognizes the crucial role of dedicated search programs in expanding our cosmic perspective. But what makes 3I Atlas truly special isn't just its interstellar origin. It's the fact that we detected it early enough to mount a comprehensive observational campaign. One Oumuamua was discovered only after it had already passed perihelion and was heading back to interstellar space, leaving astronomers with a frustratingly brief window for study. 2I Borisov offered a longer observation period, but behaved much like a typical solar system comet, limiting the insights it could provide about truly alien chemistry. 3I Atlas represents something of a golden opportunity, an active, outgassing comet from another star system, detected early enough in its approach to allow for detailed study across multiple wavelengths and observing platforms. The orbital mechanics tell a remarkable story. 3I Atlas is approaching perihelion at approximately 136 to 1.4 astronomical units from the Sun, a distance that places it between the orbits of Earth and Mars. This is close enough to receive significant solar heating, triggering the outgassing that makes comets so scientifically valuable, but not so close as to completely destroy the nucleus or make observation impossible. The timing of its closest approach to Earth in December, at roughly 1.8 astronomical units or 170 million miles, ensures that it will remain a viable target for telescopic observation even after perihelion passage. The early detection allowed for something that had been impossible with previous interstellar visitors: recovery. Astronomers began searching archival images from previous surveys, looking for earlier appearances of 3I Atlas that might have been overlooked or misidentified. These efforts paid off, extending the observational baseline back to May 2025 and providing additional data points for refining the orbital solution. Every additional observation helps constrain the uncertainty in the comet's trajectory, making it possible to predict its position with greater accuracy and plan observing campaigns more effectively. Ground-based observatories quickly joined the effort to characterize this unexpected visitor. Gemini North and Gemini South, with their 8.1-meter mirrors and advanced instrumentation, contributed crucial early observations that confirmed both the interstellar nature of the orbit and the presence of cometary activity. These initial characterization studies provided the first hints that 3I Atlas might offer something scientifically unique. Not just another comet, but one with a potentially exotic chemical composition reflecting its alien origins. The contrast with previous interstellar discoveries is striking. 1I Oumuamua, that cigar-shaped enigma, showed no obvious signs of cometary activity and exhibited unusual acceleration that sparked debates about its nature and composition. Some researchers proposed exotic explanations involving hydrogen outgassing or even artificial origins, though the scientific consensus ultimately favored natural processes. 2I Borisov, while clearly a comet, displayed chemical signatures remarkably similar to comets from our own solar system, suggesting either that comet formation processes are universal, or that it originated in a stellar environment very similar to our own Sun's. I Atlas promises to be different. Early spectroscopic observations hint at an unusually high ratio of carbon dioxide to water, a signature that would be consistent with formation in a colder or more carbon-rich environment than typical solar system comets. The coma shows signs of the characteristic green fluorescence associated with diatomic carbon, but the relative intensity and duration of this emission may provide clues about the specific organic compounds present in the nucleus. The tail development, clearly visible in recent imaging from observatories like Gemini South, appears robust and structured, suggesting active and perhaps variable outgassing from multiple regions of the nucleus. The significance of this discovery extends far beyond the excitement of finding something rare and unusual. 3I Atlas represents a direct sample of material from another stellar system, potentially carrying chemical fossils that preserve information about conditions during planetary formation around another star. The isotope ratios of elements like hydrogen, carbon, and nitrogen can reveal the temperature and irradiation environment of its birthplace. The relative abundances of different volatile compounds, water, carbon dioxide, carbon monoxide, methane, ammonia, reflect the composition and temperature structure of the protoplanetary disk from which it formed. In essence, 3I Atlas serves as an interstellar messenger, carrying news from a distant stellar nursery that we could never hope to visit directly. The message it carries is encoded in the very atoms and molecules that make up its nucleus, written in the language of chemistry and physics that scientists are only just beginning to learn to read. But like all messages from the cosmos, this one comes with a deadline. The window for decoding it is measured not in years or decades, but in the handful of months remaining before geometry and distance render 3I Atlas too faint and too distant for detailed study. The race to unlock its secrets has already begun, but the clock is ticking faster than many realize. Part 4. What it's doing right now. In the cold vacuum of space, roughly 400 million kilometers from the Sun, something extraordinary is happening to 3I Atlas, the comet that began this journey as a dark, frozen nucleus is awakening to the touch of solar radiation, transforming before our very eyes into one of the most active and scientifically valuable objects in our solar system. Recent observations from Gemini South, captured on August 27th, reveal a comet in the midst of dramatic change, developing both a substantial coma and an increasingly prominent tail that streams away from the Sun like a cosmic banner. The visual transformation is striking. Where once there was merely a point of light moving against the stellar background, we now see the classic morphology of an active comet. The coma, that fuzzy atmospheric envelope surrounding the nucleus, extends for tens of thousands of kilometers, glowing softly as sunlight excites the gas and dust particles streaming away from the solid core. The tail, still relatively modest by the standards of great comets like Hale-Bopp or Neowise, nonetheless represents clear evidence of ongoing mass loss as solar heating drives volatile compounds from the nucleus into space. But it's the details hidden within this overall picture that make 3I Atlas so scientifically compelling. The coma shows signs of developing that distinctive green tinge that comet enthusiasts know well, a color that comes from diatomic carbon molecules fluorescing under solar radiation. This isn't just a pretty visual effect. It's a direct signature of the chemical processes occurring as organic compounds in the nucleus break down and reform in the harsh environment near the Sun. The intensity and distribution of this green emission can tell us about the abundance and nature of carbon-bearing materials in the comet, providing clues about the chemical environment in which it formed billions of years ago. The speed at which 3I Atlas is moving adds urgency to every observation. At more than 130,000 mph, this interstellar visitor is covering astronomical distances in remarkably short times. Each day brings noticeable changes in brightness, coma structure, and tail development. Features that appear in one night's observations may be significantly evolved or entirely absent by the next observing run. This isn't the leisurely evolution of a typical long-period comet that might remain visible and active for months or years. This is change happening on human timescales, compressed into weeks rather than seasons. The chemical signatures emerging from spectroscopic observations are particularly intriguing. Early results suggest that 3I Atlas may have an unusually high carbon dioxide to water ratio compared to most comets from our solar system. This isn't just an academic detail, it's a potential fingerprint of the comet's alien origins. Comets formed in our solar system typically show water ice as the dominant volatile, reflecting the temperature and composition of the solar nebula from which they condensed. A comet rich in carbon dioxide relative to water might have formed in a colder environment or one where carbon chemistry dominated over the silicate and ice. Processes typical of our own stellar neighborhood, water, detection in comets typically relies on observing hydroxyl radicals, OH, molecules that form when water ice sublimates and then breaks down under solar radiation. Recent observations, including data from the SWIFT spacecraft's ultraviolet telescope, have detected what appears to be the characteristic signature of OH emission around 3I Atlas. However, the interpretation of these measurements remains somewhat contentious. Some researchers argue that the detected signals are consistent with substantial water outgassing, while others suggest that the evidence is still tentative and requires further confirmation. This scientific debate highlights one of the challenges in studying fast-moving targets. There's often pressure to publish results quickly before the object becomes too faint for further study. But this can lead to disagreements about interpretation that might normally be resolved through extended observation campaigns. What isn't in dispute is that 3I Atlas represents a natural comet exhibiting typical cometary behavior. Claims of artificial origins or exotic propulsion mechanisms, which briefly circulated in some corners of the internet following the discovery, have been thoroughly debunked by the observational evidence. The spectrum shows the expected signatures of sublimating ices and organic compounds. The morphology displays classic comet characteristics: a central condensation surrounded by a diffuse coma and a tail pointing away from the sun. The behavior follows well-understood physics of how solar heating affects volatile-rich objects. This is very much a natural phenomenon, albeit one originating from beyond our solar system. The growing tail of 3I Atlas deserves particular attention as it serves as a real-time record of the comet's activity. Cometary tails form through two primary mechanisms: radiation pressure from sunlight pushing small dust particles away from the coma, and solar wind interactions sweeping ionized gas into characteristic streamers. The relative development of dust versus gas tails can reveal information about the composition and activity patterns of the nucleus. Recent imaging shows what appears to be primarily a dust tail, suggesting ongoing erosion of solid particles from the surface as subsurface ices sublimate and create pressure that ejects material into space. The week-to-week evolution of this tail provides a window into processes occurring on and just below the comet's surface. Variations in tail brightness and structure can indicate changes in outgassing rates, possibly driven by the rotation of the nucleus exposing different regions to solar heating. Some comets exhibit jets or fans of material streaming from specific active regions, creating complex and beautiful structures in their comas and tails. While 3I Atlas hasn't yet shown clear evidence of such localized activity, the comet is still relatively far from perihelion, and more dramatic phenomena may emerge as solar heating intensifies. The timing of these observations is crucial because cometary activity isn't linear. While the overall trend follows the expected inverse square law, activity increasing as the comet approaches the sun, the details can be much more complex. Comets sometimes experience sudden outbursts brightening by factors of 10 or more in a matter of hours, as buried pockets of volatile material suddenly become exposed to solar heating. Other comets show periodic variations tied to their rotation, with jets of material streaming from active regions that face the sun during specific parts of the comet's day. Still others display long-term evolution as the outer layers of the nucleus erode away, exposing fresh material underneath the 3I Atlas. This week represents a critical phase in its observational timeline. The comet is active enough to provide clear spectroscopic targets and detailed morphological studies, but still far enough from perihelion to avoid the worst complications of solar glare and atmospheric interference. Ground-based observatories can still track it throughout much of the night, allowing for the extended integration times necessary for high-quality spectroscopy. Space-based telescopes can observe it without violating their safe-pointing restrictions that prevent observations too close to the sun, but this optimal observing window is narrowing with each passing day. As 3I Atlas continues its relentless approach toward perihelion, the geometry that currently favors detailed study will gradually shift against us. The race to extract maximum scientific value from this interstellar visitor has entered its most critical phase, with discoveries happening in real time and new results emerging from observatories around the world on an almost daily basis. Part 5. The Data Race. In observatories scattered across the globe and in the dark void of space, the most sophisticated instruments humanity has ever built are training their attention on a single, small target. The campaign to study 3I Atlas represents one of the most coordinated international efforts in modern astronomy, bringing together space telescopes, ground-based observatories, and research teams from dozens of institutions in a race to unlock the secrets of our third known interstellar visitor. The prize isn't just scientific knowledge, it's the chance to understand chemistry and processes that occur around other stars, delivered directly to our cosmic doorstep. The Hubble Space Telescope struck first in this observational campaign, using its exquisite resolution and decades of experience with solar system objects to place crucial constraints on the size of 3I Atlas's nucleus. The results were both revealing and frustrating in equal measure. Hubble's observations suggest an upper limit of approximately 5.6 kilometers for the nucleus diameter, with the possibility that it could be significantly smaller, perhaps as little as 0.32 kilometers across. This range might seem imprecise, but it reflects the fundamental challenge of studying active comets. The nucleus is completely hidden within the glowing coma of gas and dust, making direct size measurements impossible. Instead, astronomers must infer the size indirectly using models of how much material the observed coma and tail require to sustain themselves. The James Webb Space Telescope brought its revolutionary infrared capabilities to bear on August 6th, targeting 3I Atlas with the Near-Infrared Spectrograph, NIR spec. This isn't just another pretty picture, it's molecular archaeology in action. JWST's infrared vision can detect the spectral signatures of specific compounds as they sublimate from the nucleus and fluoresce in the solar radiation. The early results from this observation, still working their way through the peer review process, suggest something remarkable. 3I Atlas may indeed have an unusually high carbon dioxide to water ratio compared to typical comets from our solar system. This finding, if confirmed, would represent a genuine chemical fingerprint of alien origins. Comets from our solar system typically show water ice as the dominant volatile component, reflecting the temperature and composition conditions in the solar nebula 4.6 billion years ago. A comet with enhanced carbon dioxide content might have formed in a colder stellar environment, or perhaps in a disk with a different carbon to oxygen ratio than our own system experienced. It's the kind of measurement that can only be made with the most sensitive infrared spectrographs, and only during the brief window when the comet is active enough to produce detectable emission, lines but not so close to the Sun as to be unobservable. NASA's SphereX mission added another piece to the puzzle between August 7th and 15th, conducting its own spectroscopic survey of 3I Atlas. While SphereX is primarily designed to map the entire sky in infrared wavelengths, its ability to rapidly obtain spectroscopic data makes it valuable for studying transient objects like comets. The team has already posted preliminary research notes, and while the full analysis is still ongoing, the early indications support and extend the findings from JWST. Having multiple independent measurements of the same object is crucial in astronomy. It's the difference between an intriguing hint and a solid scientific conclusion, ground-based. Observatories bring their own strengths to this coordinated campaign. Gemini South, with its 8.1-meter mirror and suite of advanced instruments, has been tracking 3I Atlas night after night, documenting the evolution of its coma and tail with remarkable detail. The Gemini Multi-Object Spectrograph, GMOS, can simultaneously capture images in multiple filters, allowing astronomers to track how the color and brightness of different parts of the coma change over time. This kind of monitoring campaign would be prohibitively expensive with space telescopes, but ground-based facilities can revisit targets nightly, building up a comprehensive time series that captures the dynamic evolution of cometary activity. The complementary nature of space and ground-based observations cannot be overstated. Space telescopes avoid the complications of Earth's atmosphere, which absorbs crucial infrared and ultraviolet wavelengths and introduces variability that can complicate precise measurements. But they're also expensive to operate and difficult to schedule for extended monitoring campaigns. Ground-based telescopes, while limited by atmospheric absorption and weather, can provide the sustained, regular observations needed to catch transient events like sudden outbursts or the emergence of new jets from the nucleus. This is where the use everything now philosophy of the current campaign becomes evident. Mission planners and telescope schedulers are operating under the assumption that post-perihelion opportunities will be significantly more limited. While 3i Atlas will remain visible for months after its closest approach to the Sun, it will also be significantly fainter and less active. The highest quality spectroscopy, the kind needed to detect minor species and measure precise isotope ratios, requires substantial amounts of light collected over long integration times. Miss the window of peak activity and those measurements may become impossible. The spectroscopic results emerging from this campaign are revealing a complex chemical inventory. Beyond the enhanced carbon dioxide signatures, observers are detecting signs of carbon monoxide, various organic compounds, and the hydroxyl radicals that indicate water outgassing. The relative abundances of these species can provide insights into the formation temperature and irradiation history of the comet. High carbon monoxide abundance, for example, would suggest formation in extremely cold conditions where CO ice could condense and remain stable. Enhanced organic content might indicate formation in a disk rich in carbon-bearing molecules, possibly around a star with a different carbon-to-oxygen ratio than our Sun. But spectroscopy is only part of the story. Imaging campaigns are revealing the morphology and evolution of 3i Atlas's coma and tail structure. The way jets emerge and evolve can provide information about the rotation period and orientation of the nucleus. Periodic variations in brightness or coma morphology can reveal the location and extent of active regions on the surface. The structure and evolution of the tail encode information about the size, distribution, and composition of dust particles being ejected from the nucleus. Cross-calibration between different instruments and observatories is essential for building a complete picture. Hubble's size constraints must be consistent with the brightness and mass loss rates measured by other telescopes. JWST's molecular detections need to align with the overall activity levels documented by ground-based monitoring. SphereX's spectroscopic measurements should complement rather than contradict the findings from other infrared instruments. When all these pieces fit together, they form a coherent picture of what 3i Atlas is and where it might have come from. When they don't, it usually indicates that our understanding is incomplete and more observations are needed. The urgency of this campaign extends beyond mere scheduling constraints. Comets are dynamic objects with chemical and physical processes occurring on timescales ranging from hours to weeks. The composition of the coma can change as different volatile species become dominant at different temperatures. Surface features can appear and disappear as erosion exposes fresh material or buries active regions under debris. Outbursts can suddenly increase the production of gas and dust by orders of magnitude, providing valuable insights into the interior structure of the nucleus, but only if instruments are ready to capture the event. In many ways, studying 3i Atlas is like performing emergency surgery on a patient who is simultaneously moving away from you at high speed and slowly dissolving. Every measurement matters, every observation adds to the total picture, and every day that passes reduces the quality and quantity of data that can be obtained. The astronomical community has responded with remarkable coordination, sharing telescope time, data, and expertise in recognition that this opportunity may not come again for decades. Part 6. What we'll miss if we wait. The cruel mathematics of orbital mechanics and observational astronomy conspire to create a window of opportunity that closes with the inexorable precision of a countdown timer. Each day that passes without comprehensive observations of 3i Atlas represents scientific data that can never be recovered. The phenomena we might miss aren't just academic curiosities, they're the key measurements that could transform our understanding of how comets form around other stars and what conditions existed in alien planetary systems billions of years ago. Consider the jets that many comets develop as they approach perihelion. These aren't uniform outflows of gas and dust, but rather focused streams of material erupting from specific active regions on the nucleus surface. For a typical solar system comet, These jets provide crucial information about the rotation period, spin axis orientation, and distribution of volatile materials beneath the surface. They can appear and disappear on timescales of hours or days, driven by the complex interplay between solar heating, nucleus rotation, and the depth at which different ices begin to sublimate. For 3I Atlas, jets could reveal something unprecedented: how an interstellar comet responds to the first substantial solar heating it has experienced in potentially millions or billions of years. The patterns of jet activity, their timing relative to the rotation period, and their chemical composition could all provide insights into the interior structure and composition of this alien visitor. But jets are notoriously transient phenomena. They often emerge suddenly, persist for days or weeks, and then fade away as surface conditions change or active regions become depleted. The window for detecting and characterizing these jets is rapidly narrowing. As 3I Atlas approaches perihelion, the increasing solar glare will make it increasingly difficult to resolve fine details in the coma structure. By the time the comet emerges from behind the sun's glare in late November or early December, any dramatic jet activity that occurred during the period of maximum heating may have already subsided. We might be left with only indirect evidence, changes in the overall coma morphology or tail structure that hint at the spectacular displays we missed during the critical weeks when the comet was effectively unobservable from Earth. The rotation period represents another time-sensitive measurement that becomes exponentially more difficult to obtain as observing conditions deteriorate. Determining how fast 3I Atlas spins requires detecting periodic variations in brightness, coma morphology, or spectral signatures as different regions of the nucleus rotate into and out of solar illumination. This kind of photometric monitoring demands consistent observations over multiple rotation cycles, ideally spanning weeks or months to build up sufficient statistical precision. But here's the challenge. Rotation periods for small comets typically range from hours to days. Miss a few critical nights due to bad weather, telescope scheduling conflicts, or solar proximity, and you might lose the periodic signal entirely. The measurement requires not just a few snapshots, but sustained monitoring that can capture the subtle variations that repeat with each rotation cycle. As 3I Atlas approaches perihelion and becomes increasingly difficult to observe, the window for this kind of detailed temporal analysis is rapidly closing. Even more challenging are the isotopic measurements that could provide the clearest signatures of the comet's alien origins. Isotope ratios, the relative abundances of different atomic masses of the same element, serve as fossil records of the conditions under which cosmic objects formed. The deuterium to hydrogen ratio in water, for example, can reveal information about the temperature and irradiation environment in the comet's natal disk. The carbon-13 to carbon-12 ratio in organic compounds provides clues about the stellar environment and chemical processes that occurred during planetary system formation. These measurements push current instrumentation to its absolute limits. They require not just detecting the presence of specific molecules, but resolving the tiny wavelength differences between isotopologues, molecules that are identical except for the substitution of one isotope for another. The spectral lines are often weak and closely spaced, demanding both high spectral resolution and substantial integration, times to build up sufficient signal-to-noise ratio for reliable detection. The problem is that isotopic measurements become exponentially more difficult as the target becomes fainter or as observing conditions deteriorate. A spectrum that might take 4 hours to obtain under ideal conditions could require 16 hours or more when the comet is fainter or when atmospheric conditions are poor. Miss the window of optimal brightness and geometry, and these crucial measurements might become impossible with current technology. Transient molecular species present their own observational challenges. As solar heating increases, complex organic molecules in the comet's nucleus break down into simpler compounds, creating a cascade of chemical reactions that can produce dozens of different species in the coma. Some of these molecules have very short lifetimes. They form through photodissociation of larger compounds and then are quickly destroyed by further solar radiation. The result is a constantly changing chemical inventory that reflects the ongoing processing of material as it streams away from the nucleus, catching. These transient species requires being in the right place at the right time with the right instruments. A molecule that dominates the spectrum during one phase of the comet's evolution might be completely absent just days or weeks later. Some species only become detectable during specific activity phases when particular regions of the nucleus are exposed to solar heating. Others might appear only during outburst events when buried material is suddenly excavated and exposed to space for the first time in eons. The dust tail of 3I Atlas encodes information about grain properties that is equally time-sensitive. As dust particles stream away from the nucleus, they interact with solar radiation in ways that depend on their size, composition, and structure. Small particles are pushed away more rapidly by radiation pressure, while larger grains follow trajectories more closely tied to the comet's orbital motion. The result is a complex, evolving structure that can reveal details about the dust production mechanisms and the properties of the solid material being eroded from the nucleus. Color measurements of the dust tail can provide insights into grain composition and size distribution. Polarization studies can reveal information about grain shape and structure. Both types of measurements work best when the tail is well developed and the comet is bright enough for detailed photometry. As activity wanes after perihelion, the tail will gradually fade and become less structured, making these measurements progressively more difficult. Perhaps most frustrating is the knowledge that the highest quality nucleus size and shape. Constraints often come from modeling the coma structure during peak activity. The way gas and dust flow away from the nucleus carries information about the size, shape, and rotation state of the solid core hidden within the glowing coma. But extracting this information requires sophisticated models that account for the complex physics of sublimation, gas dynamics, and radiation pressure. These models work best when they have abundant observational constraints, multiple viewing angles, extended time series, and measurements across different wavelengths and activity levels. The cross-mission coordination that makes comprehensive studies possible is also schedule-bound in ways that create additional vulnerabilities. Space telescopes like Hubble and JWST operate on carefully planned observing schedules that are set months in advance. Ground-based facilities have their own scheduling constraints, complicated by weather, seasonal visibility, and competition from other high-priority targets. If one key instrument misses its observing window due to technical problems or scheduling conflicts, it can leave gaps in the multi-wavelength data set that are impossible to fill later. The stakes of these potential missed measurements extend far beyond the immediate disappointment of incomplete data sets. 3I Atlas represents only the third confirmed interstellar object in human history, and by far the most promising for detailed chemical analysis. The measurements we make or fail to make during the next few weeks will likely represent the definitive scientific legacy of this encounter. When 3I Atlas fades into the outer solar system and eventually back to interstellar space, it will carry with it any secrets we haven't managed to extract during this brief window of opportunity. In essence, we are engaged in a race against geometry, solar physics, and the fundamental limitations of our instruments. Every night of clear skies represents an opportunity to add crucial data points to our understanding. Every scheduling conflict or technical delay removes measurements from the final scientific product that can never be recovered. The window is closing, and with it, our chance to fully decode the message that this interstellar messenger has carried across the light years to reach us. Part 7. Worst case for our ignorance. History has a way of teaching us uncomfortable lessons about the cost of missed opportunities in astronomy. When 1I Oumuamua, our first confirmed interstellar visitor, tumbled through the inner solar system in 2017, It offered humanity an unprecedented chance to study material from another stellar system. The object was small, fast-moving, and unlike anything astronomers had encountered before. By the time its true nature was recognized and observing campaigns organized, Oumuamua was already racing away from the Sun, growing fainter by the day and presenting increasingly difficult observational challenges. The scientific legacy of that missed opportunity continues to haunt the astronomical community. Years later, fundamental questions about Oumuamua remain unanswered. Was it really the cigar-shaped object that initial observation suggested, or was it perhaps a flat, pancake-like body tumbling end over end? What caused the subtle but measurable acceleration that deviated from a pure gravitational trajectory? Was this acceleration due to outgassing that was simply too faint to detect directly, or did it represent some more exotic physical process? The limited observational data set collected during Oumuamua's brief visibility window left too much room for speculation and too little hard data for definitive conclusions. The contrast with 2E Borisov couldn't be more stark. Discovered in 2019 while still well outside the orbit of Mars, Borisov provided astronomers with months of optimal observing conditions. The extended observation campaign that followed revealed a wealth of information about this interstellar visitor, its size, rotation period, chemical composition, and activity patterns. Spectroscopic analysis showed that Borisov contained water, carbon monoxide, and cyanogen in ratios remarkably similar to comets from our own solar system. This finding was scientifically valuable, but also somewhat disappointing. It suggested that either comet formation processes are remarkably universal, or that Borisov happened to originate from a stellar environment very similar to our own Sun's neighborhood. The comprehensive data set obtained for Borisov demonstrates what's possible when discovery occurs early enough to mount a coordinated international observing campaign. Multiple space telescopes and ground-based observatories tracked the comet for months, building up a detailed picture of its properties and behavior. The result was not just a collection of pretty pictures, but a scientifically robust characterization that could be compared with theoretical models of comet formation and evolution. ATLAS represents our third chance to study an interstellar object and potentially our best opportunity to detect truly alien chemistry. Unlike Oumuamua, it shows clear signs of cometary activity that make detailed spectroscopic analysis possible. Unlike Borisov, early observations hint at chemical signatures that may genuinely differ from typical solar system comets. The enhanced carbon dioxide content suggested by preliminary JWST observations, if confirmed, would represent the first clear detection of compositional differences that reflect formation in a genuinely different stellar environment. But this opportunity comes with the same fundamental constraint that limited the study of Oumuamua: time. The observational window for 3I Atlas is measured in weeks, not months or years. Miss the critical period of peak activity, and we may be left with the same kind of tantalizing but incomplete data set that continues to fuel debates about Oumuamua's true nature. The difference is that this time we know what we're risking by not maximizing our observational efforts during the optimal window. Consider what happens when observational opportunities are lost due to scheduling conflicts, technical problems, or simple bad luck with weather. Jets that might reveal the rotation period and internal structure of the nucleus could appear and disappear during cloudy nights. Outbursts that briefly increase the comet's brightness by orders of magnitude might occur when all the major telescopes are pointed elsewhere. Spectroscopic signatures of rare molecules could emerge and fade during periods when atmospheric conditions make high-resolution spectroscopy impossible. Each missed observation represents more than just a data point that wasn't collected. It represents a piece of the puzzle that may never be recoverable. Comets are dynamic, evolving systems where the chemical and physical processes occurring today may be completely different from those occurring next week or next month. The specific combination of solar heating, nucleus rotation, and surface conditions that produces a particular spectral signature or morphological feature might never repeat, even for the same object. The propagation of uncertainty from incomplete data sets into scientific interpretation is particularly problematic for objects as rare and unusual as interstellar visitors. When we have thousands of well-studied comets from our solar system, a few missing measurements on any individual object rarely matter for our overall understanding. But when we have only 3 confirmed interstellar objects, every measurement carries disproportionate weight in our attempts to understand what exists beyond our solar system. Incomplete data also creates fertile ground for speculation and misinterpretation. The unusual acceleration detected for Oumuamua, combined with its elongated shape and lack of obvious cometary activity, led some researchers to propose exotic explanations involving hydrogen outgassing, artificial origins, or novel physical processes. While the scientific consensus ultimately favored natural explanations, the debates continued for years precisely because the observational data set was insufficient to definitively rule out alternative hypotheses. Isitica's atlas could face a similar fate if key measurements are missed during the optimal observing window. Suppose the enhanced carbon dioxide signatures hinted at in early observations turn out to be artifacts of observational bias or instrumental effects that only become apparent with more comprehensive data sets. Or suppose the comet exhibits unusual activity patterns or morphological features that can't be adequately characterized due to solar glare during the critical perihelion period. The result could be years of scientific debate based on incomplete information, with different research groups reaching different conclusions based on the same limited data set. The value of interstellar objects extends far beyond their individual characteristics to what they can tell us about planetary formation processes around other stars. Each visitor samples a different stellar environment and potentially a different epoch in galactic chemical evolution. The chemical signatures locked in their nuclei represent fossil records of conditions during planetary system formation that we can never observe directly. But extracting this information requires measurements of sufficient precision and completeness to distinguish between genuine compositional differences and observational artifacts. Miss the critical measurements on 3I Atlas, and we lose more than just information about this particular object. We lose a crucial data point in our broader understanding of how planetary systems form and evolve throughout the galaxy. The chemical inventory of comets reflects the temperature, pressure, and irradiation conditions in protoplanetary disks. Isotope ratios encode information about stellar nucleosynthesis and galactic chemical evolution. Dust properties reveal details about grain growth and processing in different stellar environments. But all of these insights depend on having sufficiently complete and precise measurements to draw reliable conclusions. An incomplete dataset doesn't just limit our understanding of 3I Atlas, it limits our ability to place this object in the broader context of stellar and planetary formation throughout the galaxy. We may be left wondering whether the unusual features we detected represent genuine differences from solar system objects or simply reflect the limitations of our observational campaign. The scientific method requires reproducibility and verification, but interstellar objects don't offer second chances. We can't repeat the experiment with better instruments or longer integration times. We can't go back and fill in the gaps in our data sets once the objects have faded beyond the reach of our telescopes. The measurements we make or fail to make during the brief window of opportunity represent the permanent scientific legacy of each encounter. Perhaps most troubling is the realization that our ignorance compounds over time. Each poorly characterized interstellar visitor makes it harder to understand the next one because we lack the comparative context needed to distinguish between common and unusual features. With only 3 confirmed interstellar objects, every well-characterized example is crucial for building the statistical foundation needed to understand what's typical and what's exotic in the population of objects drifting between the stars. The stakes then extend beyond mere scientific curiosity. They touch on fundamental questions about our place in the universe and the diversity of conditions under which planetary systems form. 3i Atlas offers us a chance to answer some of these questions, but only if we can extract the necessary measurements during the rapidly closing window of optimal observability. The alternative is another decade or more of speculation based on incomplete data, waiting for the next interstellar visitor to provide the missing pieces of the puzzle. Part 8. The safe but serious truth. In an era where astronomical discoveries frequently become entangled with sensationalized headlines and speculative interpretations, it's essential to establish exactly what 3i Atlas represents and what it emphatically does not. NASA's official assessment is unambiguous. This object poses absolutely no threat to Earth and will not approach closer than approximately 1.8 astronomical units during its closest passage in December. Put this in perspective, that's roughly 170 million miles, a distance that places 3i Atlas farther from Earth than the Sun is during winter months in the Northern Hemisphere. The safety assessment isn't based on wishful thinking or preliminary calculations, but on precise orbital mechanics derived from months of careful observations. As more data points accumulated from observatories around the world, the uncertainty in 3i Atlas's trajectory has steadily decreased. The object follows a well-defined hyperbolic orbit that will carry it past the Sun and back to interstellar space without any possibility of collision with Earth, Mars, or any other planet. The laws of physics that govern orbital motion are among the most thoroughly tested and reliable principles in all of science, and they leave no room for surprise encounters or last-minute course corrections. Claims of alien technology or artificial origins, which briefly circulated in some corners of social media following the discovery, have been systematically examined and dismissed by the scientific community. The spectrum of 3i Atlas shows the characteristic signatures of sublimating water ice, carbon dioxide, carbon monoxide, and organic compounds that are entirely consistent with natural cometary composition. The morphology displays classic comet features, a central condensation surrounded by a diffuse coma and a tail pointing away from the Sun due to radiation pressure. The brightness variations and activity patterns follow well-understood physics of how solar heating affects volatile-rich objects. In short, every measurement confirms that 3i Atlas is exactly what it appears to be, a natural comet that happened to form around another star. There are no anomalous accelerations like those detected for Oumuamua, no unusual spectral signatures that might suggest artificial materials, and no behavioral patterns that deviate from established cometary physics. It is, in the most literal sense, a perfectly normal comet, except for the remarkable fact that it carries chemical signatures from another stellar system. This distinction between safe and serious is crucial for understanding why the astronomical community has mobilized such extensive resources to study this object. The seriousness doesn't stem from any impact threat or exotic properties, but rather from the profound scientific value of having direct access to material from another star system. Think of it as the difference between finding a dangerous explosive device and discovering a pristine archaeological artifact from a lost civilization. One requires evacuation and bomb disposal. The other demands careful preservation and detailed analysis before the opportunity disappears forever. The scientific method provides robust mechanisms for distinguishing between extraordinary claims and extraordinary evidence. When researchers propose unusual interpretations of astronomical data, those proposals must survive rigorous peer review, independent verification, and statistical analysis. The process isn't perfect, but it has proven remarkably effective at separating genuine discoveries from observational artifacts, instrumental effects, and wishful thinking. In the case of 3i Atlas, every analysis conducted so far supports the straightforward interpretation: natural comet, interstellar origin, no threat to Earth. This doesn't mean that studying 3i Atlas lacks excitement or scientific significance. On the contrary, the chemical signatures emerging from spectroscopic analysis represent some of the most valuable data in modern planetary science. The enhanced carbon dioxide content suggested by early observations could provide insights into formation conditions around other stars. The isotope ratios, once measured with sufficient precision, may reveal information about stellar nucleosynthesis and galactic chemical evolution. The dust properties and activity patterns offer clues about surface processes and internal structure that can't be studied for any other interstellar object currently within reach of our instruments. The serious aspect of 3I Atlas lies in these scientific stakes rather than any dramatic threat scenarios. We are witnessing the delivery of a natural laboratory sample from another stellar system, complete with chemical fossils that preserve information about conditions during planetary formation billions of years ago and many light years away. The measurements we make during the next few weeks may represent our best chance for decades to understand how common the chemical conditions that led to life on Earth might be throughout the galaxy. Healthy scientific skepticism requires acknowledging uncertainty while avoiding the paralysis that comes from demanding impossible standards of proof. The preliminary findings suggesting unusual carbon dioxide abundance in 3I Atlas are based on early analysis of JWST spectroscopic data. While promising, these results require confirmation through independent observations and detailed modeling before they can be considered definitive. The scientific process is inherently iterative, with initial discoveries providing hypotheses that must be tested through additional observations and analysis. This iterative process is particularly important for interstellar objects, where the rarity of examples makes it difficult to distinguish between genuine anomalies and observational artifacts. The unusual acceleration detected for Oumuamua sparked years of debate precisely because we had no comparable objects for context. 2I Borisov provided that context by demonstrating that at least some interstellar comets behave much like their solar system counterparts. 3I Atlas offers the possibility of a third data point, potentially one that shows genuine compositional differences reflecting formation in a different stellar environment. The timeline pressure that drives current observational campaigns stems not from any imminent danger, but from the fundamental constraints of orbital mechanics and observational astronomy. As 3I Atlas approaches perihelion, the geometry that currently favors detailed observations will gradually shift against us. Solar glare will make spectroscopy increasingly difficult. The comet will become harder to resolve and track. Most importantly, the peak activity that makes chemical analysis possible will occur precisely when observational conditions are most challenging. This creates a unique convergence of scientific opportunity and temporal constraint that justifies the coordinated international effort currently underway. Space agencies and research institutions are investing substantial resources not because 3I Atlas poses any threat, but because it offers unprecedented insights into processes that occur around other stars. The running out of time narrative isn't dramatic hyperbole, it's a simple statement of observational reality. The distinction between responsible scientific communication and sensationalized speculation becomes particularly important in an era of rapid information dissemination through social media and online platforms. Early results and preliminary analyses can be misinterpreted or taken out of context, leading to overblown claims about alien visitation or existential threats. The scientific community has a responsibility to communicate both the genuine excitement of discovery and the careful, methodical process by which that excitement is channeled into reliable knowledge. For 3I Atlas, this means acknowledging both the remarkable nature of the discovery and the entirely natural processes that explain its behavior. It means celebrating the technological achievement that allows us to conduct detailed chemical analysis of material from another star system while maintaining realistic expectations about what those analyses can and cannot tell us. Most importantly, it means recognizing that the most profound questions in science, how common are the conditions that led to life, What chemical processes occur during planetary formation? How diverse are the outcomes of stellar evolution? Often have answers that are simultaneously reassuring in their adherence to natural law and awe-inspiring in their implications. For our place in the cosmos, the safe but serious truth about 3I Atlas is that it represents exactly the kind of discovery that makes astronomy so compelling, an object that poses no threat to our safety but challenges our understanding in ways that could reshape our perspective on planetary formation throughout the galaxy. The urgency isn't about survival, it's about seizing a rare opportunity to learn something genuinely new about the universe beyond our solar system. Part 9. Anatomy of an Interstellar Traveler. Stripped to its essential components, 3I Atlas presents us with a paradox wrapped in ice and dust. At its core lies a nucleus, the solid, primordial heart of the comet that Hubble's observations suggest spans somewhere between 320 meters and 5.6 kilometers in diameter. This uncertainty isn't a failure of our instruments, but rather reflects the fundamental challenge of studying an object that refuses to reveal itself directly. The nucleus remains perpetually hidden within its own atmospheric creation, shrouded in the glowing coma of gas and dust that sublimates from its surface as solar radiation slowly tears it apart. This active coma represents 3I Atlas in its current state of transformation. What began as a dark, frozen remnant from another star's planetary formation zone is now a dynamic, evolving system where ancient ices encounter solar energy for perhaps the first time in billions of years. The coma extends tens of thousands of kilometers from the hidden nucleus, glowing with the fluorescent signatures of molecules excited by solar radiation. Within this ethereal envelope, complex chemistry unfolds as organic compounds break down and reform, creating the spectral signatures that provide our only window into the comet's alien composition. The most intriguing hint of this object's extraterrestrial origins lies in those early spectroscopic measurements suggesting an unusually high carbon dioxide to water ratio. For comets formed in our solar system, water ice typically dominates the volatile inventory, reflecting the temperature and chemical conditions that prevailed in the solar nebula 4.6 billion years ago. Carbon dioxide, while present, usually plays a secondary role, but 3I Atlas appears to challenge this assumption, potentially carrying a chemical signature that speaks to formation in a colder stellar environment or around a star with a different carbon to oxygen ratio than our Sun. This finding, while still working its way through the peer review process, represents more than just an analytical curiosity. The relative abundances of different volatile species in comets serve as fossil records of the conditions under which they formed. Enhanced carbon dioxide content could indicate formation near a CO2 ice line in a protoplanetary disk, or perhaps processing by stellar radiation that selectively preserved carbon dioxide while depleting water ice. Either scenario would provide direct evidence that the chemistry of planetary formation varies significantly between different stellar systems. The water story itself remains somewhat contentious, highlighting the challenges of extracting definitive conclusions from observations of rapidly evolving targets. Spectroscopic detection of water in comets typically relies on identifying hydroxyl radicals, OH, molecules that form when water ice sublimates and subsequently breaks down under solar radiation. Recent observations, including data from Swift's ultraviolet telescope, have detected what appears to be the characteristic 308.5 nanometer emission line of OH near 3I Atlas. However, the interpretation of these detections involves complex modeling assumptions about the production and destruction rates of OH in the comet's coma. Some researchers argue that the observed signals are consistent with substantial water outgassing, comparable to levels seen in solar system comets. Others contend that the evidence remains tentative, requiring additional observations and more sophisticated modeling to establish definitive water abundances. This ongoing scientific debate illustrates the challenges inherent in studying fast-moving targets where there's limited time for the kind of comprehensive analysis that would normally resolve such questions. What's not in dispute is the growing prominence of the green coloration in 3I Attilis' coma, a visual signature that connects this interstellar visitor to fundamental processes occurring in comets throughout the universe. This distinctive green glow comes from diatomic carbon molecules, C2, that form when more complex carbon-bearing compounds in the nucleus break down under solar heating. The liberated carbon atoms can combine to form C2, which then fluoresces at specific wavelengths. When excited by solar radiation, the intensity and distribution of this green emission provides clues about the abundance and nature of organic materials in the comet's nucleus. Strong C2 emission suggests a substantial inventory of carbon-bearing compounds, potentially including complex organics that could offer insights into prebiotic chemistry in other stellar systems. The temporal evolution of the green color, how it brightens and fades as the comet approaches and recedes from perihelion, can reveal information about the distribution of organic materials within the nucleus and the processes by which they're liberated and processed in the coma. The tale of 3I Atlas tells its own story about the ongoing transformation of this ancient relic. Gemini South's GMOS imaging has documented the steady growth and evolution of the tail as solar heating intensifies. This isn't just a static streamer of material, but a dynamic structure that encodes information about the size, distribution, composition, and ejection mechanisms of dust particles leaving the nucleus. The way the tail curves and evolves provides insights into the balance between radiation pressure, which pushes small particles directly away from the Sun, and gravitational forces that try to keep material bound to the comet's orbital path. Analysis of the tail's color and morphology can reveal details about dust grain properties that are impossible to measure directly. Larger grains tend to remain closer to the nucleus and follow trajectories more closely tied to the comet's orbital motion. Smaller particles are more efficiently accelerated by radiation pressure, creating the characteristic curved tail structure that points away from the Sun. The color of different parts of the tail can indicate variations in grain composition or size distribution, providing clues about the processes occurring at the nucleus surface. Rotation and jet activity represent the next frontier in understanding 3I Atlas's behavior. Many active comets develop jets, focused streams of gas and dust that emerge from specific regions on the nucleus surface. These jets can appear and disappear as the nucleus rotates, creating periodic variations in brightness and coma morphology that reveal the comet's spin rate and axis orientation. For 3I Atlas, detecting such variations could provide crucial constraints on the nucleus's physical properties and internal structure. The challenge is that jet detection requires sustained, high-cadence observations over multiple rotation periods. Cometary nuclei typically rotate with periods ranging from hours to days, creating subtle variations that can be detected only through careful photometric monitoring. As 3I Atlas approaches perihelion and becomes increasingly difficult to observe due to solar glare, the window for this kind of detailed temporal analysis is rapidly narrowing. Some analyses of 3I Attilis' orbital characteristics suggest it may originate from older populations of stars in our galaxy, the thin or thick disk, components that formed during earlier epochs of galactic evolution. If confirmed, this would imply that the comet preserved ice chemistry from a time when the galaxy's overall composition differed from present conditions. The isotope ratios and molecular abundances locked in its nucleus could provide direct insights into stellar nucleosynthesis and chemical evolution over cosmic time. However, this kind of galactic archaeology requires measurements of exquisite precision that push current instrumentation to its limits. Determining the comet's age and origin requires not just detecting the presence of various molecules, but measuring their precise isotope ratios and relative abundances. Such measurements demand substantial integration times under optimal observing conditions, exactly the kind of observations that become increasingly difficult as 3I Atlas approaches perihelion and solar glare begins to interfere with spectroscopic analysis. The anatomy of this interstellar traveler then reveals itself to be a complex layering of ancient preservation and ongoing transformation. At its heart lies a nucleus that may be billions of years old, carrying chemical fossils from the earliest epochs of planetary formation in another stellar system. Surrounding this ancient core is a dynamic atmosphere of sublimating gases and organic molecules currently being processed and modified by solar radiation in ways that both reveal and obscure the comet's primordial composition. Understanding 3I Atlas requires decoding this interplay between preservation and change, between ancient chemistry and current physics, between what the comet was when it formed in distant darkness and what it's becoming as it encounters our sun's energy. The measurements being made today capture only a snapshot of this ongoing transformation, but that snapshot may represent our best chance for decades to understand the diversity of chemical processes that occur during planetary formation throughout the galaxy. Part 10. The Geometry Squeeze. The universe operates according to laws that care nothing for human convenience or scientific schedules. As 3I Atlas hurtles toward its October 29th perihelion at a distance of roughly 1.36 to 1.4 astronomical units from the Sun, the same orbital mechanics that make this encounter scientifically valuable also create an observational nightmare that will test the limits of our most sophisticated instruments and observing strategies. From Earth's perspective, the approach to perihelion creates a geometric squeeze that gradually transforms 3I Atlas from an ideal target into an increasingly difficult challenge. The fundamental problem lies in the three-body dance between Earth, Sun, and Comet. As the comet approaches its closest solar distance, it appears from our vantage point to move progressively closer to the Sun in our sky. This isn't because 3I Atlas is actually heading toward the Sun from our direction, but because of how the angles work out as all three objects move through their respective paths in space. For ground-based telescopes, this geometric evolution presents fundamental limitations that no amount of advanced technology can overcome. Professional observatories have strict safety protocols that prevent pointing their instruments too close to the Sun, typically no closer than about 30 to 40 degrees, depending on the specific telescope and local atmospheric conditions. These restrictions exist for good reason. Solar radiation can damage sensitive detectors, while scattered sunlight overwhelms the faint signals from astronomical targets. As 3I Atlas approaches perihelion, it will gradually enter this forbidden zone of sky, becoming effectively invisible to the ground-based facilities that currently provide the bulk of our observations. The timing of this geometric squeeze couldn't be more frustrating from a scientific standpoint. Comets typically exhibit their most dramatic and scientifically interesting behavior precisely during the period around perihelion when solar heating reaches its peak intensity. This is when outgassing rates maximize, when new volatile species may become detectable, when jets and other morphological features often reach their most prominent development. For 3I Atlas, this period of maximum activity will coincide almost exactly with the weeks when traditional optical and infrared observations become increasingly difficult or impossible. Space-based telescopes offer some relief from these geometric constraints, but they come with their own limitations and challenges. The Hubble Space Telescope can observe closer to the Sun than ground-based facilities, typically down to about 50 degrees from the solar direction. The James Webb Space Telescope, with its sophisticated sunshield and thermal management systems, can point even closer to the Sun while maintaining the ultra-cold temperatures needed for its infrared detectors to function optimally. But even these capabilities have limits, and both telescopes operate under strict, safe pointing restrictions that prevent observations when targets are too close to our star. Moreover, space telescopes are precious and limited resources that must balance observations of 3I Atlas against dozens of other high-priority scientific programs. Unlike ground-based facilities that might dedicate entire nights to comet monitoring, space telescopes typically observe targets in carefully planned sequences that maximize scientific return across their full suite of objectives. Securing extended observing time for 3I Atlas requires demonstrating not just scientific value, but urgent scientific necessity that justifies displacing other planned observations. The geometry becomes even more complex when we consider what happens after perihelion. While 3I Atlas will eventually emerge from behind the Sun's glare and become observable again in late November or early December, it will do so under significantly changed circumstances. The comet will be past its peak activity, potentially much fainter, and exhibiting different physical and chemical behavior as solar heating diminishes. Most importantly, the closest approach to Earth, occurring in December at about 1.8 astronomical units, happens well after perihelion, when the comet may be in a declining rather than intensifying phase of activity. This creates a cruel irony in the observational timeline. The period when 3I Atlas is closest to Earth and therefore brightest and most easily observable corresponds to a phase when it may be less active and less scientifically informative than during the earlier approach to perihelion. It's like being offered the best seats in the theatre after the main performance has already ended and the actors are taking their final bows. Before the solar glare becomes overwhelming, however, 3I Atlas offers one tantalizing possibility for close-range observations. On approximately October 3rd, the comet will pass within about 0.19 astronomical units of Mars, roughly 30 million kilometers. This presents a unique opportunity for spacecraft currently in orbit around Mars to obtain observations from a completely different vantage point, potentially avoiding some of the geometric constraints that limit Earth-based observations. Mars orbiters like ESA's Mars Express, NASA's Mars Reconnaissance Orbiter, and the Mars Atmosphere and Volatile Evolution mission weren't designed for deep space observations, but they carry cameras and spectrometers that might be capable of detecting and characterizing 3I Atlas during its relatively close passage. The European Space Agency has confirmed that mission planners are investigating the feasibility of such observations, though the technical challenges are substantial. Pointing spacecraft instruments away from Mars toward a fast-moving target requires careful trajectory planning and may conflict with primary mission objectives. Even if Mars-based observations prove feasible, they would provide only a brief snapshot of 3I Atlas from a different perspective. The real value would lie in obtaining simultaneous observations from both Mars and Earth, creating a form of parallax measurement that could help constrain the comet's size, activity distribution, and three-dimensional structure in ways that single-point observations cannot achieve. The post-perihelion reacquisition strategy represents a careful balance between optimism and realism. Observatories around the world are already planning campaigns to pick up 3I Atlas again as it emerges from solar glare in late November or early December. The geometry at that time will be more favorable for extended observations, with the comet visible during dark hours and well separated from the Sun in Earth's sky. However, this improved geometry comes at the cost of reduced activity and brightness as the comet moves away from peak solar heating. Ground-based facilities are preparing for this second phase of observations, with the understanding that they may be documenting the aftermath of processes that occurred during the unobservable perihelion period. Changes in coma morphology, tail structure, or overall brightness could provide indirect evidence of outbursts, jet activity, or other phenomena that occurred when direct observation was impossible. It's a bit like arriving at a crime scene after the perpetrator has fled. The evidence may tell a compelling story, but it's necessarily incomplete compared to witnessing the events directly. Space-based telescopes face similar challenges during the post-perihelion phase. While the improved geometry makes observations safer and more straightforward from a technical standpoint, The reduced activity and brightness of 3i Atlas may push some measurements beyond the sensitivity limits of current instruments. Spectroscopic analysis that was challenging, but feasible during the approach to perihelion, may become impossible as gas production rates decline and spectral lines weaken. The timing constraints become even more critical when we consider the coordination required for multi-wavelength observations. Ideally, scientists want to observe 3i Atlas simultaneously across multiple wavelengths: visible light for overall morphology and activity, infrared for molecular signatures and dust properties, ultraviolet for specific atomic and molecular transitions. This requires synchronized observations from multiple facilities, each operating under their own constraints and limitations. During the approach to perihelion, this coordination becomes increasingly difficult as different facilities reach their solar avoidance limits at different times. Ground-based optical telescopes may lose the target first, followed by infrared facilities with only space-based instruments capable of maintaining observations closest to perihelion. The result could be a patchwork of observations from different instruments at different times, making it difficult to correlate simultaneous phenomena across multiple wavelengths. Perhaps most concerning is the possibility that some of the most scientifically valuable moments may occur during the period when 3i Atlas is effectively unobservable. Comets sometimes experience dramatic outbursts during their closest approach to the Sun, when buried volatile materials are suddenly exposed to intense solar heating. These events can brighten a comet by several magnitudes in a matter of hours, creating spectacular displays of jets and enhanced tail development. If such an outburst occurs during 3i Atlas's passage through the zone of solar glare, we might detect its effects only indirectly through changes visible in post-perihelion observations. The tail might show evidence of enhanced dust production. The overall brightness might be elevated compared to pre-perihelion predictions, or the chemical composition of the coma might reveal the signature of newly exposed materials. But the outburst itself, the moment of most intense activity and scientific interest, would remain hidden behind the Sun's overwhelming glare. The geometry squeeze thus represents more than just a technical challenge for observers. It embodies a fundamental tension between the physical processes that make comets scientifically interesting and the observational constraints that limit our ability to study those processes. The very solar heating that drives cometary activity also creates the geometric conditions that make observation difficult. The periods of peak scientific value coincide almost precisely with the periods of minimum observational accessibility. This situation demands careful, strategic planning and realistic expectations about what can be achieved during each phase of the observational campaign. Pre-perihelion observations must focus on establishing baseline properties and detecting early signs of activity evolution. The limited observations possible near perihelion should target the most critical measurements that absolutely require peak activity levels. Post-perihelion campaigns need to document the consequences of whatever occurred during the unobservable period while the comet remains bright enough for detailed study. The broader lesson of the geometry squeeze extends beyond 3i Atlas to the general challenge of studying transient astronomical phenomena. The universe doesn't schedule its most interesting events for our observational convenience. Solar eclipses occur when and where orbital mechanics dictates, not when astronomers have optimal weather conditions. Supernovae explode in distant galaxies regardless of telescope availability or funding cycles, and interstellar visitors approach perihelion according to the laws of celestial mechanics, not the constraints of human schedules and instrumental limitations. Adapting to these constraints requires both technological innovation and strategic flexibility. New generations of space-based telescopes with enhanced solar avoidance capabilities could extend the observational window closer to perihelion. Automated survey systems might provide earlier warning of future interstellar visitors, allowing more time for comprehensive observational campaigns. International cooperation could ensure that observational assets are positioned optimally to maximize coverage during critical periods. But for 3i Atlas, these future improvements offer no help. The geometry squeeze is already underway, with the observational window narrowing day by day as the comet continues its relentless approach toward perihelion. The race against geometry has entered its final phase, where every clear night represents a valuable opportunity, and every scheduling conflict or technical delay removes irreplaceable data from the final scientific legacy of this encounter. Part 11. Can we catch it? The fantasy is irresistible. A spacecraft racing through the void to intercept 3i Atlas, deploying instruments directly into the comet's coma, sampling the pristine ices and organic compounds that have drifted unchanged through interstellar space for eons. Such a mission would revolutionize our understanding of chemistry beyond our solar system, providing direct laboratory analysis of materials that formed around another star. But the harsh mathematics of orbital mechanics and spacecraft propulsion quickly transform this dream into a sobering lesson about the limitations of current technology and the importance of advanced planning. Launching a spacecraft after discovery to intercept 3i Atlas requires changes in velocity, delta V in the language of mission planners, that far exceed the capabilities of any existing or planned propulsion system. The comet is moving at over 130,000 orbital relative to the Sun, following a hyperbolic trajectory that will carry it completely out of the solar system. Matching this velocity and trajectory would require accelerating a spacecraft to speeds comparable to the fastest objects ever launched by humanity, but with the additional challenge of precise navigation to rendezvous with a small, rapidly moving target. Even if such extreme velocity changes were technically feasible, the energy requirements would be staggering. Current chemical propulsion systems, which power all interplanetary missions, operate close to their theoretical efficiency limits. Ion drives and other electric propulsion systems can achieve higher exhaust velocities, but at the cost of extremely low thrust levels that make rapid trajectory changes impossible. Nuclear propulsion, while potentially offering higher performance, remains largely in the development phase and would require years of additional engineering before deployment on operational missions. The fundamental problem is that interstellar objects don't announce their presence with convenient advance notice. 3i Atlas was discovered in July 2025, just 3 months before its perihelion passage. Even if a suitable spacecraft had been sitting ready for launch, there wouldn't have been enough time to plan the mission, conduct final preparations, and execute the complex trajectory required for rendezvous. Deep space missions typically require years of advanced planning, with launch windows determined by orbital mechanics rather than human schedules. This sobering reality has led mission planners to think differently about how to study future interstellar visitors. Rather than attempting to chase objects after discovery, the strategy emerging from agencies like the European Space Agency involves pre-positioning assets in space, ready to respond rapidly when opportunities arise. The most ambitious example of this approach is the Comet Interceptor mission, scheduled to launch in 2029 to L2 Lagrange Point 2, where it will wait in a kind of cosmic parking spot for a suitable target to present itself. Lagrange Point 2, located about 1.5 million kilometers from Earth in the direction away from the Sun, offers several strategic advantages for a standby interception mission. Spacecraft positioned there remain in a stable gravitational balance between Earth and the Sun, requiring minimal fuel to maintain their position. The location provides excellent communication with Earth while offering a vantage point that makes most of the solar system accessible for rapid trajectory changes. Most importantly, objects at L2 can wait for years if necessary, monitoring the sky for suitable targets while conserving fuel and maintaining instrument readiness. The Comet Interceptor mission represents a new paradigm in planetary exploration. Build first, then wait for the right target to appear. The spacecraft consists of 3 separate probes designed to fly through a comet's coma from different angles, creating a 3-dimensional picture of the comet's structure and activity. The main spacecraft carries cameras for high-resolution imaging, spectrometers for chemical analysis, and instruments for measuring magnetic fields and plasma properties. Two smaller probes will separate during the encounter, providing additional perspectives and sampling different regions of the coma. The scientific goals of Comet Interceptor align perfectly with what we would want to achieve with 3i Atlas if such an encounter were possible. High-resolution imaging could reveal surface features and active regions on the nucleus with detail measured in meters rather than kilometers. Mass spectrometry could provide direct chemical analysis of coma gases without the complications of Earth's atmosphere or the distance limitations of remote spectroscopy. Dust analysis could determine the size, composition, and structure of particles being ejected from the nucleus. Plasma and magnetic field measurements could characterize how the comet interacts with the solar wind environment it's encountering for the first time. The Comet Interceptor strategy acknowledges that we can't predict when or where the next interesting comet will appear, but we can be ready to respond rapidly when one does. The mission is designed to target either a long-period comet making its first approach to the Sun or an interstellar visitor like 3i Atlas. In either case, the science goals focus on studying pristine materials that haven't been heavily processed by repeated solar heating. I-Atlas thus serves as a proof of concept for the Comet Interceptor approach. It demonstrates both the scientific value of interstellar objects and the frustrating limitations of trying to study them exclusively through remote observations. The chemical signatures that we're struggling to interpret through Earth-based and space-based spectroscopy could be definitively identified through direct sampling. The nucleus size and structure that remain hidden within the glowing coma could be revealed through close-up imaging. The activity patterns and outgassing mechanisms could be observed directly rather than inferred from distant observation. But Comet Interceptor also illustrates the timescales involved in developing the capabilities needed to study interstellar visitors properly. The mission was conceived partly in response to the scientific frustrations of the Oumuamua encounter when the object was discovered too late for comprehensive study. The spacecraft won't launch until 2029, nearly 12 years after Oumuamua's discovery and 4 years after 3i Atlas's perihelion passage. Even then, it may wait at L2 for years before a suitable target appears. This highlights a fundamental tension in space exploration between the pace of technological development and the unpredictable timing of natural phenomena. We can plan and build spacecraft to study asteroid impacts, but we can't predict when or where those impacts will occur. We can design missions to investigate cometary outbursts, but we can't schedule those outbursts for our convenience. We can prepare for the next interstellar visitor, but we don't know when it will arrive or what trajectory it will follow. The lesson of 3i Atlas is that rapid response capabilities require advanced preparation on timescales measured in decades rather than months. The spacecraft that will intercept the next interstellar visitor is probably already being designed, though we don't yet know what object it will study or when that encounter will occur. The instruments that will revolutionize our understanding of interstellar chemistry are likely in development now, waiting for their chance to analyze samples from another star system. In the meantime, 3i Atlas serves as both inspiration and frustration, a tantalizing glimpse of what direct investigation could reveal, accompanied by the sobering knowledge that such investigation remains just beyond our current reach. The comet carries with it not just chemical signatures from another star system, but also a challenge to the space exploration community to develop the capabilities needed to study its successors more comprehensively. The race to catch 3i Atlas is already over. We never had a realistic chance to win it, but the race to catch the next interstellar visitor has already begun, with missions like Comet Interceptor representing humanity's best strategy for seizing future opportunities that we're currently forced to watch slip away. The question isn't whether we can catch 3i Atlas, but whether we'll be ready when its successor arrives. Part 12. Near-term flyby ideas. While launching a dedicated mission to intercept 3i Atlas remains beyond current capabilities, the astronomical community has begun exploring more creative possibilities that could provide at least some close-up observations of this interstellar visitor. These proposals, ranging from the technically challenging to the nearly impossible, illustrate both human ingenuity and the lengths to which scientists will go to squeeze additional data from rare opportunities. Though none offer the comprehensive investigation that a purpose-built mission would provide, even partial success could yield valuable scientific insights that complement the remote observations being conducted from Earth. The most ambitious of these proposals involves NASA's Juno spacecraft, currently orbiting Jupiter and conducting detailed studies of the gas giant's atmosphere, magnetosphere, and internal structure. Mission analysts have investigated whether Juno could be redirected to intersect 3i Atlas's trajectory in March 2026, when the comet will be well past perihelion but still potentially observable. The concept is audacious. Use Jupiter's gravity to bend Juno's trajectory toward an intercept course, transforming a planetary orbiter into an impromptu comet interceptor. The technical challenges are formidable. Juno's fuel reserves were designed for orbital operations around Jupiter, not for the large velocity changes required to escape the planet's gravitational influence and pursue a target in a completely different part of the solar system. The spacecraft's instruments, while sophisticated, were optimized for studying Jupiter's environment rather than cometary phenomena. The communication systems would need to maintain contact across vast distances while the spacecraft potentially moves far from Earth. Most critically, any attempt to redirect Juno would effectively end its primary mission at Jupiter, trading proven scientific returns for a high-risk, high-reward gamble on a target that might be too faint or inactive for meaningful study by March 2026. Despite these challenges, the concept has generated significant interest because Juno carries several instruments that could provide unique insights into 3i Atlas if an encounter proved feasible. The spacecraft's camera system could obtain close-up images of the nucleus and coma structure. Its radio science experiment could probe the internal density distribution through gravitational measurements. The magnetometer could characterize how the comet interacts with the interplanetary magnetic field. Most intriguingly, Juno's microwave radiometer might be able to peer through the coma to study thermal emission from the nucleus itself, potentially revealing information about internal composition and structure. Mars offers another potential platform for opportunistic observations, though with significantly more modest scientific goals. The October 3, 2025 flyby of 3i Atlas past Mars at approximately 30 million kilometers presents a unique viewing geometry that could complement Earth-based observations. ESA mission planners have confirmed they are exploring the possibility of redirecting Mars Express and other orbiters to observe the comet during this close passage. The Mars-based observations would face their own set of technical constraints. The spacecraft were designed to study Mars and its atmosphere, not to track fast-moving objects in deep space. Pointing instruments away from Mars toward 3i Atlas requires careful planning to avoid conflicts with primary mission objectives. The cameras and spectrometers aboard these spacecraft weren't optimized for the low light conditions and specific wavelengths most useful for cometary studies. Nevertheless, even basic photometry and imaging from the Mars perspective could provide valuable constraints on the comet's size, activity level, and coma structure. More speculative proposals have emerged from detailed orbital analyses suggesting that other deep space missions might pass relatively close to 3i Atlas's trajectory at various points during the coming months. The Psyche mission en route to study a metal-rich asteroid, and the JUICE spacecraft heading toward Jupiter's moons both follow paths that bring them within a few tenths of an astronomical unit of the comet's orbit at different times. While these distances are still enormous by terrestrial standards, tens of millions of kilometers, they're close enough that mission planners have at least investigated whether useful observations might be possible. The reality of such proposals quickly bumps against the harsh constraints of deep space operations. Spacecraft carry limited fuel for trajectory adjustments, and any significant deviation from planned paths could jeopardize primary mission objectives that represent years of development and hundreds of millions of dollars in investment. Instruments designed for specific targets and environments may not function optimally when pointed at completely different objects under different conditions. Communication and data relay systems optimized for particular orbital geometries might struggle to maintain contact during unexpected maneuvers. Perhaps more importantly, even successful opportunistic observations would provide only snapshot glimpses of 3I Atlas rather than the sustained monitoring needed to understand its evolution and behavior. A flyby encounter lasting hours or days can't capture the gradual changes in activity, coma development, and chemical composition that unfold over weeks and months. The most scientifically valuable observations often require extended time series that reveal how cometary processes respond to changing solar heating and environmental conditions. Nevertheless, these near-term flyby proposals serve important functions beyond their immediate scientific potential. They demonstrate the space exploration community's willingness to think creatively about maximizing scientific return from unexpected opportunities. They provide valuable experience in rapid mission planning and adaptive operations that could prove crucial for future encounters with unpredictable targets. They highlight both the capabilities and limitations of current deep space assets, informing the design of future missions that might be better equipped for rapid retargeting. The proposals also illustrate the value of maintaining a diverse fleet of spacecraft throughout the solar system. While none of the current missions were designed specifically to study comets, their distributed presence creates opportunities for observations from multiple perspectives and distances that wouldn't be possible from Earth alone. This serendipitous capability argues for maintaining active missions even after their primary objectives are complete, since they provide platforms for studying unexpected phenomena that arise unpredictably. For the broader public following the 3I Atlas story, these speculative mission concepts provide a tangible connection between abstract astronomical observations and the human exploration of space. While most people will never have the opportunity to observe the comet through professional telescopes or interpret spectroscopic data, they can easily understand the drama of potentially redirecting a spacecraft from its primary mission to chase an interstellar visitor. The proposals tap into the same sense of adventure and exploration that drives human space exploration, even when the technical realities make success unlikely. The ultimate value of these near-term flyby ideas may lie not in what they accomplish with 3I Atlas, but in how they prepare us for future opportunities. Each proposal that gets developed, even if never implemented, advances our understanding of what's possible with current technology and what improvements would be most valuable for future missions. They force mission planners to think about rapid response capabilities and adaptive operations in ways that could prove crucial when the next interstellar visitor arrives. Most importantly, they maintain scientific engagement and public interest during the period when traditional observational opportunities are becoming more limited. As 3I Atlas approaches perihelion and becomes increasingly difficult to study through conventional means, these alternative approaches keep alive the possibility that we might still learn something new from this remarkable visitor from another star system. Even if none of the proposals ultimately prove feasible, they represent the kind of bold thinking that drives scientific discovery and space exploration forward. Part 13, If We Had More Time. In the realm of scientific imagination, unlimited time and resources transform 3I Atlas from a fleeting observational target into the subject of the most comprehensive interstellar investigation ever attempted. If we could design the perfect mission to study this alien visitor, unconstrained by the realities of launch windows, propulsion limitations, or budget considerations, what would such an endeavor look like? The answer lies in pushing current and future technologies to their limits, creating a multi-spacecraft armada capable of extracting every possible insight from humanity's third confirmed sample of material from another star system. The ideal mission would begin with Comet Interceptor as a starting point, but expand far beyond its current design. Rather than a single 3-probe encounter lasting hours, imagine a sophisticated orbital campaign that could accompany 3I Atlas for months, documenting its evolution from a relatively inactive ice ball to a fully developed active comet and back to dormancy. Such a mission would require revolutionary advances in propulsion, technology, perhaps nuclear-powered systems that could match the comet's extreme velocity and maintain formation flight throughout its passage through the inner solar system. The scientific payload for such a dream mission would read like a catalogue of cutting-edge analytical techniques, high-resolution imaging systems capable of resolving surface features on the nucleus down to meter-scale resolution would map the topography, identify active regions, and document how surface morphology changes as volatile materials sublimate away. These aren't just pretty pictures, they're geological surveys of a world that formed around another star, potentially revealing impact craters from interstellar debris, structural features that encode the comet's formation history, and active processes that have never been observed directly on any solar system body. The COCA imaging system planned for Comet Interceptor represents current state-of-the-art, but our hypothetical mission would advance far beyond it. Multispectral imaging across wavelengths from ultraviolet to thermal infrared would simultaneously map surface composition, temperature distribution, and volatile outgassing patterns. Stereo imaging from multiple spacecraft would create three-dimensional models of the nucleus, revealing its true shape and internal structure. Time-lapse imaging over complete rotation periods would document how jet activity, surface features, and volatile loss patterns change as different regions experience solar heating. Spectroscopic analysis would reach unprecedented levels of sophistication. The MERMIS instrument concept, covering wavelengths from 0.9 to 25 micrometers, would provide thermal imaging and spectroscopy simultaneously, mapping temperature variations across the nucleus surface while identifying specific minerals and ices. But our dream mission would go further, incorporating laser-based spectroscopy that could perform chemical analysis of individual dust grains, isotope ratio measurements with precision rivaling Earth-based laboratories, and real-time monitoring of chemical reactions occurring in the coma as organic compounds break down and reform under solar radiation. The mass spectrometry capabilities would be truly revolutionary. While Comet Interceptor's MANIAC instrument will provide basic chemical analysis of coma gases, our enhanced mission would carry multiple mass spectrometers optimized for different types of measurements. High-resolution instruments could distinguish between isotopologues, molecules with different isotopic compositions, providing direct constraints on formation temperature and stellar nucleosynthesis processes. Time-of-flight systems could analyze dust grain composition with unprecedented precision. Ion trap spectrometers could study complex organic molecules that might preserve information about prebiotic chemistry in other stellar systems. But perhaps the most scientifically valuable aspect of an extended mission would be the ability to perform controlled experiments on an interstellar comet. Imagine deploying small landers or penetrators that could sample subsurface materials, drill cores from the nucleus, or even trigger controlled outgassing events to study how the comet responds to artificial heating. Such experiments could reveal the internal structure and composition distribution in ways that remote observations never could. The dust and fields instrumentation would map the three-dimensional structure of magnetic fields and plasma properties throughout the comet's environment. These measurements would reveal how interstellar material interacts with the solar wind for the first time, potentially providing insights into magnetic field preservation during interstellar travel and the processes by which comets acquire and lose volatile materials during their journey between stars. An ideal mission timeline would span multiple years, rather than the brief encounters possible with current technology. Early phases would focus on characterizing the nucleus while it's still relatively inactive, mapping surface features and composition before they become obscured by coma development. As the comet approaches perihelion, the mission would document the onset and evolution of activity, tracking how different volatile species become dominant at different temperatures and how the surface morphology changes as materials sublimate away. The most scientifically valuable period would be near perihelion itself, when 3I Atlas reaches peak activity. This is precisely when current observational constraints make detailed study most difficult, but our hypothetical mission could maintain close proximity throughout this critical phase. Multiple spacecraft could sample different regions of the coma simultaneously, creating a three-dimensional map of chemical composition and physical properties. High-speed imaging could capture individual jets and outbursts as they occur, revealing the processes by which buried materials become exposed and processed. Post-perihelion observations would document how the comet winds down from peak activity, potentially revealing different layers of material as surface erosion exposes progressively deeper regions of the nucleus. Long-term monitoring could determine whether 3I Atlas shows any signs of structural damage from its encounter with solar heating, or whether it remains intact and capable of surviving indefinitely in the interstellar medium. The sample return component of such a mission would be the ultimate prize. While technically far beyond current capabilities, the ability to return physical samples of 3I Atlas to Earth for laboratory analysis would revolutionize our understanding of interstellar chemistry. Earth-based laboratories could perform analyses impossible aboard spacecraft, precise isotope ratio measurements, complex organic chemistry, crystallographic studies of mineral phases, and detailed microscopic examination of dust grain structure. Such samples would represent the first confirmed extraterrestrial materials from beyond our solar system, a complement to the meteorites and lunar samples that currently comprise our collection of space materials. The scientific return would justify almost any cost, providing direct laboratory constraints on stellar nucleosynthesis, interstellar chemistry, and planetary formation processes that we can currently study only through remote observations and theoretical modeling. The broader impact of such a comprehensive investigation would extend far beyond cometary science. Understanding the detailed chemistry and structure of 3I Atlas would provide ground truth for interpreting observations of comets around other stars, which are beginning to be detected by advanced telescopes. The isotope ratios and chemical signatures would serve as calibration standards for understanding stellar evolution and galactic chemical evolution. The organic compounds and their distribution patterns could inform theories about the delivery of prebiotic materials to planetary systems. But perhaps most importantly, such a mission would demonstrate humanity's capability to conduct sophisticated scientific investigations throughout the solar system and beyond. The technological advances required, high-performance propulsion, miniaturized analytical instruments, autonomous navigation and operations, would have applications far beyond comet science. The mission would serve as a stepping stone toward eventual interstellar missions that could study other star systems directly. Of course, the reality is that we don't have unlimited time or resources for studying 3I Atlas. The comet operates on its own schedule, approaching perihelion according to the laws of celestial mechanics rather than human convenience. But the exercise of imagining what we could accomplish with ideal capabilities serves an important function. It defines the goals toward which future mission development should strive and identifies the technological advances that would provide the greatest scientific return. For 3I Atlas specifically, we must work with the capabilities we have and the time remaining before geometry renders detailed observations impossible. But for the next interstellar visitor, we can begin now to develop the technologies and mission concepts that would enable the kind of comprehensive investigation that 3i Atlas deserves. The dream mission scenario isn't just fantasy, it's a roadmap for the future of interstellar science. Part 14, The Next Visitor. The discovery of 3i Atlas represents more than just the identification of another interstellar object. It signals the beginning of a new era in astronomy where such visitors may become regular rather than exceptional events. As our survey capabilities improve and our understanding of the interstellar object population grows, we can expect future discoveries to arrive with the kind of advance notice that makes comprehensive scientific campaigns not just possible, but routine. The question isn't whether another interstellar visitor will arrive, but when and whether we'll be ready to seize the opportunity more effectively than we could with 3i Atlas. The technological foundations for this improved readiness are already being laid through next-generation survey programs that will revolutionize our ability to detect distant moving objects. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, will begin operations in the coming years with capabilities that dwarf current asteroid and comet detection systems. Its massive camera will image the entire visible sky every few nights, building up a comprehensive movie of everything that moves against the stellar background. Unlike current surveys that might detect interstellar objects only months before perihelion, Rubin Observatory could potentially spot them years in advance while they're still in the outer solar system and barely beginning to show signs of activity. This extended lead time would transform our ability to plan and execute observational campaigns, moving from rushed, opportunistic observations to carefully coordinated multi-year studies that could track the complete evolution of interstellar visitors from dormancy through peak activity and back to quiescence. The strategic implications of early detection extend far beyond simply having more time to observe. With years of advance notice, mission planners could design and launch dedicated spacecraft specifically tailored to study individual interstellar objects. Rather than repurposing existing missions or attempting rapid trajectory changes, space agencies could develop purpose-built interceptors optimized for the specific characteristics and orbital parameters of each target. The result would be scientific returns orders of magnitude greater than anything possible with current hasty response. Capabilities: space-based infrared telescopes represent another crucial component of future interstellar object investigations. Ground-based facilities, no matter how sophisticated, face fundamental limitations from atmospheric absorption that blocks crucial wavelengths needed for detailed chemical analysis. The James Webb Space Telescope has already demonstrated the power of space-based infrared spectroscopy for 3i Atlas, but JWST is a general-purpose observatory that must balance comet observations against dozens of other scientific priorities. Future. Dedicated infrared survey missions could monitor interstellar objects continuously throughout their passage through the solar system, tracking chemical changes as solar heating triggers the sublimation of different volatile species. Such observations would reveal how interstellar ices respond to solar radiation for the first time in potentially billions of years, providing insights into preservation mechanisms during interstellar travel and the diversity of volatile inventories in different stellar systems. Ground-based networks are evolving to provide rapid response spectroscopy and photometry that could catch transient events like outbursts within hours of their occurrence. Current facilities often require days or weeks to schedule observations of new targets, by which time brief outbursts or other dynamic phenomena may have already ended. Automated systems that can recognize and respond to sudden changes in brightness or activity could capture these events as they happen, providing insights into the physical processes that trigger sudden increases in cometary activity. The coordination challenges that currently complicate multi-facility observations of 3i Atlas could be addressed through improved data standards and automated scheduling systems. Rather than manually coordinating observations between different telescopes and research groups, Future campaigns could operate through centralized systems that optimize observing schedules across multiple facilities, ensuring comprehensive coverage while minimizing conflicts and gaps. Planetary orbiter missions represent an underutilized resource for studying interstellar visitors from unique vantage points. The Mars flyby opportunity for 3i Atlas illustrates how spacecraft already positioned throughout the solar system could provide valuable complementary observations if they could be rapidly retargeted. Future mission designs could incorporate greater flexibility for such opportunistic science, perhaps carrying general-purpose cameras and spectrometers that could study unexpected targets even when they differ significantly from primary mission objectives. The scientific return from improved interstellar object investigations extends far beyond simply collecting more data about individual visitors. Each well-characterized interstellar comet provides a sample of material from a different stellar environment, potentially representing different epochs in galactic chemical evolution. The isotope ratios and chemical signatures preserved in these objects serve as fossil records of stellar, nucleosynthesis and planetary formation processes occurring throughout the galaxy over billions of years. Understanding the population characteristics of interstellar objects could reveal fundamental insights about planetary system formation and evolution. Are carbon dioxide-rich comets like 3i Atlas common or exceptional? Do different stellar environments produce systematically different comet compositions? How do the chemical signatures of interstellar visitors compare with theoretical models of planet formation around different types of stars? These questions can only be answered through statistical analysis of multiple well-characterized objects, making each future detection increasingly valuable for building a comprehensive understanding of interstellar chemistry. The first few interstellar objects serve primarily to establish that such visitors exist and can be studied. The next few dozen will begin to reveal patterns and variations that constrain theoretical models of stellar and planetary evolution, educational and public engagement. Opportunities multiply with each interstellar discovery. While 3i Atlas has generated significant scientific interest, public awareness remains limited compared to more visually spectacular astronomical events. Future interstellar visitors detected earlier and studied more comprehensively could become focal points for public education about stellar evolution, planetary formation, and the search for life beyond our solar system. The development of rapid response interceptor capabilities, exemplified by missions like Comet Interceptor, represents perhaps the most important advancement for future interstellar science. Rather than watching helplessly as visitors race through the inner solar system faster than we can mount comprehensive investigations, pre-positioned spacecraft could provide the kind of detailed, up-close analysis that transforms speculation into definitive knowledge. Budget and policy considerations will play crucial roles in determining how effectively we can exploit future opportunities. The coordination required for comprehensive interstellar object campaigns spans national boundaries and institutional jurisdictions in ways that challenge traditional funding and management structures. International cooperation will be essential, but it must be planned and implemented in advance, rather than improvised during the brief windows when opportunities arise. The technological advances required for optimal interstellar object science, higher performance propulsion, miniaturized analytical instruments, automated observation systems have applications far beyond cometary studies. They represent stepping stones toward more ambitious goals like interstellar missions to nearby star systems or comprehensive surveys of objects in the outer solar system and beyond. Perhaps most importantly, the framework being developed for studying interstellar visitors could serve as a template for investigating other types of transient astronomical phenomena. The same rapid response capabilities, coordinated observation networks, and flexible spacecraft operations that optimize interstellar object science could be applied to studying asteroid impacts, stellar occultations, or other unpredictable events that require immediate response and coordinated action. The next interstellar visitor will arrive according to the laws of orbital mechanics and cosmic chance rather than human schedules or scientific priorities. But unlike the situation with 3i Atlas, we don't have to wait passively for that arrival. The groundwork being laid now, improved survey capabilities, rapid response missions, coordinated observation networks will determine whether humanity's fourth confirmed interstellar encounter represents another frustrating glimpse of what might have been or the beginning of a new era in our understanding of the galaxy beyond our solar system. The clock is already running toward that future encounter, and the preparations we make today will determine whether we're ready to seize the opportunity when it arrives. Part 15, Final Hourglass. The sand continues to fall through humanity's cosmic hourglass, each grain representing another hour, another day in our narrowing window to decode the secrets carried by 3i Atlas. Today, as we count down the final weeks to October 29th perihelion, the urgency that began as a distant concern has transformed into an immediate reality, shaping every decision made in observatories around the world. The geometry of space and time has become our most implacable adversary, indifferent to human curiosity and scientific ambition alike. What we know with certainty forms a foundation both reassuring and tantalizing. 3i Atlas is undoubtedly a natural comet, displaying all the classic signatures of sublimating ices and organic compounds under solar heating. No exotic propulsion mechanisms, no artificial materials, no evidence of intelligent design, just the ancient processes of chemistry and physics playing out on a stage lit by our sun's radiation. It poses no threat to Earth, following a trajectory that will carry it safely past our planet at a distance of roughly 170 million miles in December, farther away than we are from the sun during Earth's winter months. Yet within this reassuring framework of natural processes lies chemistry that may be genuinely alien to our solar system experience. Hubble's observations constrain the nucleus to somewhere between 320 meters and 5.6 kilometers in diameter, a frustrating range that reflects the fundamental challenge of studying an object perpetually shrouded in its own atmospheric creation. The James Webb Space Telescope and SphereX have detected what appears to be an unusually high carbon dioxide to water ratio, a potential fingerprint of formation conditions around another star. The growing green fluorescence in the coma speaks to diatomic carbon molecules fluorescing under solar radiation, while the evolving tail documents ongoing mass loss as ancient ices encounter stellar energy for perhaps the first time in billions of years. But certainties fade quickly into a landscape of questions that may never receive definitive answers. The water detections remain contentious, with different research groups reaching different conclusions based on the same observational data. Some argue that hydroxyl radical signatures indicate substantial water outgassing comparable to solar system comets. Others contend that the evidence remains tentative, requiring additional observations and more sophisticated modeling to establish reliable abundances. This scientific debate illustrates both the challenges inherent in studying fast-moving targets and the honest uncertainty that accompanies measurements pushed to the limits of current instrumentation. The rotation period of 3i Atlas remains unknown, though determining it could reveal crucial insights into the nucleus's shape, internal structure, and distribution of active regions. Jets and other morphological features that could encode this information require sustained monitoring over multiple rotation cycles, exactly the kind of extended observational campaign that becomes increasingly difficult as solar glare begins to interfere with detailed observations. Miss this measurement now, and it may remain forever locked away in the spinning nucleus of a comet racing back toward interstellar space. Fine-scale structure in the coma and tail, potentially encoding information about dust grain properties and outgassing mechanisms, demands the kind of high-resolution imaging and spectroscopy that works best under optimal observing conditions. As 3I Atlas approaches perihelion and becomes increasingly difficult to resolve against the sun's glare, these subtle details may fade beyond the reach of even our most sophisticated instruments. The coordinated international campaign that has mobilized to study this visitor represents a remarkable convergence of scientific capability and institutional cooperation. Hubble Space Telescope, James Webb Space Telescope, SphereX, and ground-based facilities from Gemini South to observatories across multiple continents have focused their attention on this single small target racing through the inner solar system. The level of coordination and resource allocation reflects not just scientific curiosity, but recognition that opportunities to study interstellar visitors arrive unpredictably and depart according to schedules we cannot control. Yet even this unprecedented mobilization faces fundamental constraints that no amount of international cooperation can overcome. Space telescopes operate on schedules planned months in advance, with complex trade-offs between different scientific priorities and safety requirements that prevent observations too close to the sun. Ground-based facilities must contend with weather, atmospheric conditions, and the gradually worsening geometry as 3I Atlas approaches solar conjunction. The most sophisticated coordination cannot extend the observational window beyond what orbital mechanics allows. The debates surrounding tentative measurements reflect a broader challenge in studying objects that don't wait for peer review cycles or extended analysis. The pressure to publish results quickly before targets become too faint for further study can lead to disagreements about interpretation that might normally be resolved through extended observational campaigns. For 3I Atlas, we must balance the need for rapid dissemination of results with the scientific requirement for careful, methodical analysis. This tension between urgency and accuracy embodies the fundamental challenge of transient astronomy. The universe presents its most interesting phenomena on schedules that care nothing for human convenience or scientific methodology. Solar eclipses occur when orbital mechanics dictates, not when weather conditions are optimal. Supernovae explode in distant galaxies regardless of telescope availability, and interstellar visitors approach perihelion according to the laws of celestial mechanics, not the constraints of observational astronomy. The broader scientific value of 3I Atlas extends far beyond its individual characteristics to what it represents for our understanding of planetary formation throughout the galaxy. Each interstellar visitor samples a different stellar environment, potentially carrying chemical signatures that reflect the diversity of conditions under which planetary systems form and evolve. The isotope ratios and molecular abundances preserved in these ancient ices serve as fossil records of stellar nucleosynthesis and disk chemistry that we can never observe directly. But extracting this information requires measurements of sufficient precision and completeness to distinguish genuine compositional differences from observational artifacts or instrumental effects. Or incomplete data sets don't just limit our understanding of individual objects, they limit our ability to place those objects in the broader context of galactic chemical evolution and planetary system diversity. The observational legacy of 3I Atlas will ultimately be determined by what we manage to accomplish during these final weeks before perihelion renders detailed study increasingly difficult. The measurements we make or fail to make during this closing window will represent the permanent scientific record of humanity's third encounter with confirmed interstellar material. Every clear night represents an irreplaceable opportunity to add crucial data points to our understanding. Every scheduling conflict or technical delay removes measurements from the final scientific product that can never be recovered. The window is closing not gradually, but with the relentless precision of orbital mechanics, where small changes in geometry compound rapidly into insurmountable observational challenges. The hourglass, a metaphor that has guided our exploration of 3I Atlas, isn't merely dramatic framing, it reflects the genuine temporal constraints that shape every aspect of this investigation. Unlike laboratory experiments that can be repeated with better equipment or longer integration times, unlike nearby astronomical objects that remain available for study across multiple observing seasons, interstellar visitors offer single opportunities that must be seized completely or lost forever. As October 29th approaches and the geometry squeeze tightens its grip on our observational capabilities, 3i Atlas continues its transformation from pristine interstellar relic to active comet and eventually back to dormancy. We are witnessing processes that may not have occurred for millions or billions of years: ancient ices encountering stellar radiation, organic compounds breaking down and reforming, surface features emerging and disappearing as volatile materials sublimate away. The universe has delivered to our cosmic doorstep a sample of material from another star system, complete with chemical fossils that preserve information about conditions during planetary formation in distant places and ancient times. But this delivery comes with an expiration date measured not in years or decades, but in the handful of weeks remaining before geometry relegates 3i Atlas to the realm of the unobservable. Curiosity, as we have learned, operates under deadline pressure in ways that transform abstract scientific interest into urgent practical necessity. The questions we ask about 3i Atlas aren't just intellectually interesting, they're temporally constrained in ways that make delay equivalent to permanent loss of information. The final grains of sand continue to fall through our cosmic hourglass, marking time in a countdown that cares nothing for human schedules or scientific ambitions. When the last grain falls and 3i Atlas disappears behind the sun's glare, we will be left with whatever we have managed to measure and understand during this brief window of opportunity. The sky, as always, will not wait for us to be ready. In the end, 3i Atlas will carry away with it not just the chemical secrets of another star system, but also a sobering reminder of the constraints under which all astronomical discovery operates. We study the universe on its terms rather than our own, seizing opportunities when they arise and accepting the limitations imposed by the laws of physics and the geometry of space and time. The countdown continues, relentless and precise, toward a conclusion that was determined by celestial mechanics billions of years before human civilization began to wonder about our place among the stars. What we learn in the time remaining will have to suffice, because time, like the comet itself, waits for no one. The window is closing not gradually, but with the relentless precision of orbital mechanics, where small changes in geometry compound rapidly into insurmountable observational challenges. The hourglass, a metaphor that has guided our exploration of 3i Atlas, isn't merely dramatic framing, it reflects the genuine temporal constraints that shape every aspect of this investigation. Unlike laboratory experiments that can be repeated with better equipment or longer integration times, unlike nearby astronomical objects that remain available for study across multiple observing seasons, interstellar visitors offer single opportunities that must be seized completely or lost forever. As October 29th approaches and the geometry squeeze tightens its grip on our observational capabilities, 3i Atlas continues its transformation from pristine interstellar relic to active comet and eventually back to dormancy. We are witnessing processes that may not have occurred for millions or billions of years: ancient ices encountering stellar radiation, organic compounds breaking down and reforming, surface features emerging and disappearing as volatile materials sublimate away. The universe has delivered to our cosmic doorstep a sample of material from another star system, complete with chemical fossils that preserve information about conditions during planetary formation in distant places and ancient times. But this delivery comes with an expiration date measured not in years or decades, but in the handful of weeks remaining before geometry relegates 3i Atlas to the realm of the unobservable. Curiosity, as we have learned, operates under deadline pressure in ways that transform abstract scientific interest into urgent practical necessity. The questions we ask about 3i Atlas aren't just intellectually interesting, they're temporally constrained in ways that make delay equivalent to